Is it 10 now, Santosh? Can you hear me? Okay. Okay, good morning, everyone. So I think I'm going to give a set of 3 lectures today, tomorrow, I think, and day after, I guess. On galaxies, a little bit broad. So this would be an introduction to galaxies in general, not too specific on particular galaxies, if you know them. And we will try to see at the end of this introduction how we can understand, sort of going to get into the physics of galaxies, because that's where we would like to, that's how we'd like to understand from your perspective. And this is a picture where an exploration by Hubble Space Telescope, the so-called the Hubble Ultra Deep Field, and this is one of the what you see on the right side is an image of a piece of sky in the southern hemisphere, and just a moment. And each of these like dots are more or less like the galaxies from the deep field. Many of them, like now, if you see the fainter galaxies, they're like quite far away from us. And so this is one of the this image, or this millions of galaxies like that are found in this apparently blank part of the sky. This is the pointing in the southern hemisphere, okay, near the Fornax cluster, and this is basically known as the Hubble Deep Field, but this is in a bigger patch of the sky, which is the Chandra Deep Field South, okay, in which Hubble Deep Field is a small, tiny part of a patch of the sky there. And that's where, like, you see, like, it's basically it's almost like a pencil beam going to the very small patch of the sky and going for a deep observation. Okay, like several, many tens of orbits of like Hubble, and those images are like coded, and you see very deep images. Deep in a sense, you can see fainter and fainter objects in this image. Okay, and fainter objects, maybe they are farther and farther away, and so this opened up our understanding of galaxies from the past. Some of these images that you see, this is like from the Nick Moss and the Wide Field Camera 3 in the infrared band, and you see how the galaxies look like at redshift 7. Okay. They are, of course, we cannot say how the galaxies look like, but what you see is like a part of the play between the instrumentational limitation, okay, because obviously we cannot see galaxies that we see in the local universe, okay, but if you think about very high redshift, very galaxies that are early universe. This is, for example, redshift 7, when the universe was just 650 million years old. Okay, and you see the infrared camera. This is how some of these galaxies are. So there are like various examples of these galaxies. For example, this is one patch of the deep field. This is another deep field, and you see how the galaxies looks like. So this is a redshift 7.7, which is a Lyman break galaxies. If I have time, I will try to explain to you what is Lyman break galaxies and how do we detect them. Okay, so so there are amazing this early universe picture of our galaxies, and another interesting part which you would see here is this set of galaxies which are called the Tadpole Galaxies, where you see there is a head and there's a tail, there's a head and the tail, the head and the tail. It's like that. The head is is beaming with star formation. Okay, so they're very bright, followed by a tail. It's almost like a comet-like feature in the anyway. This is around redshift 1 and 2. I'm hoping that you understand what is redshift. Okay, it's in some sense like redshift 1 would be when the universe was half its age, so around 8 billion years, 7 to 8 billion years. And the redshift 1 and 2 were also a very a special epoch in the history of the star formation history of the universe, when the universe star formation history sort of peaked and this redshift range between redshift 1 and 2. Okay, redshift 0 is now, and higher and higher redshift you go to the earlier and earlier universe. Okay, and 13.6 billion years is now, and then you go to like t is equal to 0. Look at that. Okay, so in this sense, what we say is this good the Hubble deep field is you can see the universe age of the universe that we are probing with HST is around a billion years. Okay, so within around, so it's like few hundred mega years around. So of course, like you want to go as far as possible in the early universe, but let's see. Coming to the how the galaxies looks like when they are sort of at a bit lower redshift. Okay, we call lower redshift compared to redshift 6, 7, and you see this is z equals to 1.47, 1.41, 1, and all the way up to 0.5. You can see that. Not a very clear, all the structures looks very fuzzy and thick arms, and like this is what I call by like thick arms. These are like thick arms. Okay, this is like a spiral here. This is like definitely but that's in a high redshift. So they are you will see the difference in the when you compare to the local universe galaxies. So coming back to from this early universe to our Milky Way. Okay, this is the image of a Milky Way galaxy. Okay. This is Andromeda and this is M33. Okay, this is Andromeda and M33. So these three sort of these galaxies, or the spiral galaxies, if you like, they are actually form the major part of the local group, but then associated to each of these big galaxies like Andromeda, Milky Way, there are many satellite galaxies or like the dwarf galaxies around them, which are smaller in mass and size and same as velocity. So this would be the picture, artist impression of our Milky Way galaxy. So give you a so this should be applicable to almost all the most of the spiral galaxies in the local universe, and you can see that's the big image that we show is the artistic impression of the Milky Way, and the sun is located at 8.5 kiloparsec from the center and is going around the Milky Way. Is orbiting around the Milky Way in the anti-clockwise direction with a velocity at the location of the sun, which is around 220 kilometers per second. Okay, and at the center, what you see is basically an elongated structure, which is the light. Light comes from the stars, so it's a starlight, and the elongated structures are called the bar. Okay, so many galaxies in the local universe and probably also in the early universe, which we don't know because of the resolution. So they are of this kind, of the Milky Way kind. Okay, not in terms of a mass, but in terms of how they look, which is the morphology. Okay, and this is the first constructed image of the Milky Way. Okay, with the sun at the center. Okay, made by Herschel in 1785. So from here to here is like more than 200 years. Right, more than 200 years it took from this sun-centric Milky Way image to all the way go up to the actual picture of the Milky Way galaxy. So if you look at the morphology, then various kinds of galaxies are there, okay, in the local universe. And in the local universe now we can see many things very clearly. Okay, which means if you look deeply here, this is like image of a bar galaxy. But if you see these like faint structures here, these are basically the dust layer. Okay, dust layer coming into like a different location. This is a characteristic. And if you look like clearly, so you can see like there are many star forming region. Okay. Then if you look at here, there's a bar. There seems to be some kind of over density in starlight. Okay. And then there are galaxies which looks like in edge-on view. So if you like look at the face-on, okay, so it's like this. So you see like the spiral, but the same galaxy, if you look at like this, they will look like an elongated object in the sky, but they are different from this one and different from this one. Okay, for example, in this one, in the center, there is no bright patch, which is generally called the bulge of the galaxy. In this case, this is called the boxy bulge. If you just carefully look in the Milky Way, this is the image taken by the COBE satellite, okay, and constructed image in the infrared. Okay, so this is also again not a direct image, which you can imagine we cannot image the galaxy, but it's a reconstructed image from the COBE satellite observations in the infrared. Okay, why I came there? So these also, if you look at in the central structure, they look like a box, and they also look like a box here. So there are many galaxies. Or Milky Way is known to have this kind of structure, so many other galaxies, but some don't. Okay, you can see here that it's very flat, extremely thin. These are known as super thin galaxies, so they don't make this central structure. So if I believe in the so in some sense, what we do basically by looking at this individual feature structures is that we get clues, okay, about various. So okay, I'll repeat it again. So what we do is you pick up this small events. For example, in this case, this did not form bulge. This form a very central light, so it's like there is a bulge. You can obviously ask a question: why this galaxy didn't have a bulge? Why this galaxy have a bulge? So then you are basically trying to address the question about the formation scenario of these galaxies. So it is extremely important to look into the detailed morphology of each of these galaxies, and what we do is basically we try to classify them accordingly. So there is a class of galaxies which are very flat, super thin. There's a class of galaxies which are with the boxy bulge. There's a class of galaxies which are round bulge. This is a taxonomy in astronomy. So you get to see various kinds of shapes and size. I believe it's in other branches probably also, which are closer to in the biology. So there is a need for classification. This thing. So by looking into this, there is a need for classification. For example, you would not say that this one and this one are the same. Although this is a long, thin, long bar, this also seems like there's a elongated. Sorry. So there is a round thing at the center, cloud, and then this seems like a handle here. Okay. And they are not obviously this is connected, but these and these are definitely not connected, except that there's a spiral structure, but the central structures are really different. Okay? So reason I'm saying all this is there is a huge amount of these galaxies available on the internet now. So there's a huge database available. So you guys can just go pick up and try to look morphology. Maybe I'll see if I have slides on that. Now there's an interesting thing that we said. We came from the local group in which we saw that there are 3 main galaxies and there are the dwarf satellites. Okay. So the other cases, as you move on, this is a cluster of galaxies, Abel 2744, and you can see that the galaxies actually also live in different environment. It's a cluster environment, so they are not isolated. So I believe you had already heard from Shomak about this. And then this is a coma cluster picture, but I wanted to show you this. When you talk about the morphology of the galaxies, okay, this you see here, and this part up to this part, you could see with a normal telescope, but this is what you see is a diffuse light, right, which goes all the way extend to very far away radius. Okay. This is the new stuff that you're seeing coming from a deep imaging technology. Okay, where you take images over a longer period. It's not just the period, but there are other instrumental development and the improvement are there, which allows you to pick up these faint structures of light around. And someone would say that in this case, if you say the galaxy ends here, because the starlight is where the galaxies are, and where the starlight is not there. So now, if you say go fainter in the sky, so we go below, which if you can, then you see the galaxy extends far beyond. So the question that comes to your mind or I or everyone is how far the galaxy extends, or what is the real size of a galaxy, right? So that's another interesting thing which you can answer or try to answer the question. So this is a group of the galaxies. They are very important because if we see towards the line, end of the line of this talk, that galaxies live in dense environment, and then they are not all galaxies are isolated. That's the picture that I wanted to give. And if it is in group environment where there is only few galaxies, then there is something called the relaxation time, which is shorter and which lets galaxies almost hustle and bustle together. So they interact. Okay, so they interact more efficiently than in cluster, than in isolated. In isolated galaxy, there is nobody to interact. So there is no tidal interaction with another galaxy unless there is a flyby encounters. Okay. Then there is a cluster of galaxies in which all galaxies are going around in its own orbit about the center of the cluster. And there is also the chances that you interact with other galaxies very little. I'll come to that. We can show this mathematically. And then there's a group of galaxies. These are interesting objects, if you say. This is the aggregate of this galaxy system, which is the group of galaxies, few galaxies less than 10. So they are very efficient in interaction. So they are very useful for understanding. Now, going through this crash course of galaxies from the very early universe to now, local universe. So this is what you probably have seen. And this Hubble classification scheme that is what I was talking about. So if you for example, look at this galaxy, this is the bar spiral, so SBB, then SA means, so you can see the CBA0. C means the arms, spiral arms are wide open. Okay. If you look at a galaxy in which this is like a C, okay, you can have another, okay, like more like closed. So it should be like a B, C, and then you see A in which it's like almost tightly wound. Okay, this kind of schematically you can say this is A and this is 0. So this is a sequence in which means in this case there's no spiral structure. Okay, so which means so this is a different class of galaxies which is called the lenticular galaxies or S0 galaxies. And as you go from here to here, all the way, the spiral arms are open. It's like more open and open. Okay, I hope you understand the sense of openness, because we can actually, for example, if you think about this, most tightly wound spiral galaxy, in some sense, in this spiral would be like, okay, this will be like a most tightly wound spiral structure. So it's like a very, very tightly wound. Okay, so it should be close to like, of course, A. But yeah, so that's, by looking at this, you can like, classify it, to put it into this bucket, put it in the B bucket, C bucket, A bucket, like that. And then you can also distinguish galaxies from this is as a bar, this doesn't have bar, so there is only like a central bright structure. Okay. And then on this side, there are galaxies which are called the elliptical galaxies, in which this is E0, E1, E2 up to E6. So greater than E6 do not exist for reasons of instability. And this 0, 1, 2, 3 means that imagine you take an elliptical galaxy in the sky, like an image, and then you can actually measure the semi-major axis A, semi-minor axis B in projection. Okay, just like that in the sky. So you feed like one ellipse at the outer boundary, and you can calculate En is equal to 10 times 1 minus B by A. When B is equal to A, N is equal to 0. So this is basically called En. All right. So En means which tells you that as it goes from 1, 2, 3, 4, it gets more and more flattened and flattened. Okay. Otherwise, it could be like the round E0 galaxy. Now, as you will see, just a moment, what I wanted to show. Now, this is this Hubble classification scheme that you see. So there are two things here. One is, first of all, we want to understand galaxies as a different class. So in this case, bar galaxy would be a class, spiral galaxy would be a class, S0 galaxy would be a class, then E0 galaxy would be, E elliptical galaxy would be as a class, and then there is irregular galaxy, which we don't have any the like obvious shape and size, so they are irregular. Now, there's an interesting thing that the question is that what we know is in the local galaxies. So now we look at the bright galaxies in the sky, and I put in like where we know everything very well. Okay. Now I have already shown you the highest redshift galaxies, and then come to the local. Now question is how far these Hubble classification scheme exists, or this is called the tuning fork diagram. How far away the tuning fork diagram exists, right? When did it start, the tuning fork diagram? Okay, so that's one of the questions that people try to understand nowadays, and it is also like a kind of directive. So it means that in other words, if you look that when exactly this morphology and this thing first appeared, okay, or maybe there's a chance that you would say that okay, you may find a galaxy with the morphology. Maybe I'll show you. But at that time of the universe, that slice of the universe, like in the time, was there like an Hubble tuning fork diagram? Okay, that's the question. So this gives you basically a way to understand how does these structures and the morphology evolve over time. Okay, so to do this, so this is the spectroscopically confirmed spiral galaxy, the highest redshift spiral galaxy at redshift like 2.18. Okay, this appeared in Nature in almost like 10 years ago. And so the question about the Hubble tuning fork diagram that goes to that how when did the first spiral structure appear in galaxies? Okay, was it redshift 2? Was it redshift like even earlier? So we don't know very well this question unless like we have many such observations like this redshift 2 and maybe beyond. We know it very well. Okay, so this really depends on with a very high quality telescope and the spectroscopic measurements, which will allow you to sort of identify the spiral structure. You can see the actual image in HST infrared band 160 around 1.6 micron is like almost like this. There is a spiral structure. Yeah, so it is like that. So this whole game together to basically see that what we would like to achieve is that how do these high redshift galaxies from the high redshift they evolve towards the local galaxy. Okay. So what are the mechanisms? So various mechanisms are already there. Okay, if you look at this high redshift galaxies, which look like a clumpy and that looks like a very irregular shape, which you cannot put it into the Hubble tuning fork diagram for obvious reason. And these are the galaxies around redshift 1 to 2. They're dominant of this kind. Okay. Now, local galaxies look much more matured and well developed. Okay. Now, the question is what shapes the galaxies from this early universe to now? If there's early universe, in my cases, is like when you are seeing galaxies in some sense, like at least you see some clouds, at least some structures. Okay, not just like one block, but that's also okay. So in this case, from there to here, it's like it will take a lot of probably time and effort for us, but on the parallelly, there's this cosmological and body simulation goes on, and that has a many different parts of the world are active in developing this cosmological hydro simulation in which the structure forms and they form the galaxies. by putting various physics into it, and many of them have contributed in sort of this understanding. So overall, there are element like what physics actually governs there. So it could be the accretion of gas. So the galaxies like that, as it form from this clumpy phase, maybe they would accrete a lot of gas. They may merge with another small galaxy, small clumps merge with the bigger one. They grow big, and then of course there is a lot of star formation. Remember the stars that we see in a galaxy at a particular redshift, they may be formed in situ, or they may have been accreted from another satellite or a merger. So that's the thing. So the understanding the star formation is very important. So hopefully, if you have curiosity and send me questions so that I can next time talk about it, because there are too many things to talk. So I do not know where you should see. So the star formation is very important. So combination of the star formation and the merger activity. Another important aspect of this thing is that when you look at a galaxy, imagine so it's like some kind of structure here, you see. Okay. The question that comes is that if you see stars here, of course you see in starlight. Okay. It would be coming from contribution from the SFR, the star formation process, plus the margin. I don't write as a. This is what we measure. Like we see an image in the sky and we measure them, right? But we know that this can be either from the star formation which formed from the gas which is there, and gas condensed and formed stars. It could be also that it formed from the minor merger where already formed star or clump came into picture, like this, there, joined. Okay. The question is, how do I quantify from here? Right? How do I quantify from here? Okay. So we need, because once the merger happens in a galaxy, you don't see the signature anymore. I mean, it's not like sometimes you see disturbed environment, but if it is a minor merger, it when you say minor merger, then the ratio is 10. If the host mass is 10 times the, imagine 10 m, m is the mass of the host galaxy, then it should be 1 m. Okay, so it's like a big galaxy gobbling up one small satellite, and once the satellite gets in, nothing much happens. Within a short time, everything erased as if nothing happened. Okay, so that's a property in which the galaxies work. So this is all possible to do with mathematics, but let's wait for today. So the question is, this SFR, the star formation and the minor mergers, so this gets erased, so we don't see actually. Okay. You look more or less like normal galaxies, like what you see at redshift 0, z equals to 0. This galaxy, can we say that how much star has formed from the star formation alone and with the minor merger? So this requires you to know the star formation history, which is a very difficult quantity as well. Now, how the star formation has evolved over time, from early time to now. And then minor mergers probably is difficult because we don't know how many galaxies it gobbled up over the time. It came from this redshift 2-ish to now. Okay, it's a really, really difficult problem. Okay, but we always try to work in this and then see if we can quantify the star formation history and the star formation in the galaxy from various avenues, various facts that we know about the galaxies, bits and pieces of puzzle put together and sort of quantify them, and maybe we can quantify how many mergers it happened. I'm talking about observationally. This is perfectly possible in if you are doing, for example, cosmological hydrodynamical simulation, where you put each one of them as a recipe actually. So you say that there is a recipe for star formation, there is a recipe for like gas accretion maybe, and then inflows, outflows, various stuff that you can like now think about in physics. We can put it as a recipe into the cosmological simulation, and sort of see that simulation produces real like galaxies, and they are very successful in recent times, and lots of things that we think we understand are from there as well. But when you talk about the observation, like you look at the sky, you want to know the evidence, direct evidence of everything. So this is and then from the evidence you want to like prove this stuff and move ahead and say, okay, yes, we understand. Because no matter what, until and unless you see in the sky and try to deduce from there, satisfaction is like a bit far. Okay. So we sort of understand a very basic first, okay, and we get into a little bit of what can be measured in a galaxy. Okay. Now this obviously like is a very basic, and you see, imagine now what I plan to do is basically I want you to get familiarized with the distribution of light in a galaxy and quantify how many stars in the galaxy there, and eventually try to see like the physics of the galaxies, like what galaxies are actually. Of course, before we get into, we already know like what galaxies are, like because you have seen lots of like images, pictures of them. Okay, they are morphologically look very different. Okay, now what other things are there to understand in that? Of course, we can say that the galaxies are made up of stars. Okay, because we see the starlight. Then you have gas. Gas can be of H1 plus H2, neutral hydrogen gas and the molecular hydrogen gas. Then you have dark matter, which is invisible. We don't know, but we infer it from the from the velocity measurement. Okay, so and of course, like there can be also like the black hole at the center of the galaxy, which is like almost all galaxies now are shown to have a black hole, supermassive black hole at the center of the galaxy. So these are what the galaxy is composed of. Okay, but in a typical normal galaxy, if you take a Milky Way kind of galaxy, 90% of mass is in the stars, and then 10% is in the gas. So this is basically of the visible matter. Of the visible matter. Visible matter means the thing that we can measure, okay, with an astronomical instrument. Okay, so so 90% of them stars, and the rest are basically gas, which is like H1 and H2. Okay. If you go to different galaxies, like different, not the Milky Way kind of. Milky Way is in S, B, C type. But if you go to evenlet type and other galaxies, then this fraction changes. Okay, that's not very important at the moment. We need not go into that detail. So these galaxies, what you see here, there is a starlight. Okay, the starlight. So the flux that you see, if you know the luminosity, then it should be basically L by 4 pi d square. Okay, and then if you say that, okay, let's look at from a small tiny patch of the sky on the image, and you say that you measure with your telescope at the distance d, then you see that way I calculate is that the surface brightness is basically the flux from this and the solid angle it subtends, which is just for this distance, which is delta r by d, capital D. So it should be like a theta, so it's like theta squared. And from this, the surface brightness becomes independent of distance. Independent of distance d from us to the galaxy. Okay. Of course, like there are as you go, if you go to very far and far away from us, then the curvature effect becomes important, and the surface brightness as a function of r. This r is like this radius r is proportional to 1/1 plus z to the power 4. Z is the redshift of the galaxy. Redshift is like how far away the galaxy is, and this is called the surface brightness dimming, Tolman dimming, various kinds. So there is like you can see like dimming of the surface brightness, which means the actual if it is coming from a redshift, a high redshift, you see by this factor it dims, which means the actual is like not that much bright. So you have to take care of this into account. But let's like that's a very higher order thing. But what we measure is that if you take a galaxy, if I give you an image of a galaxy, then you see the surface brightness at a radius r from the center, if you talk about the circular radius, or it could be also an ellipse. If you fit an ellipse, then it should be like a semi-major axis. So this surface brightness is independent of distance from the galaxy to us, and once you measure the surface brightness, you can actually calculate the total light within this in projection. This, imagine this is in projection. This is not an actual. That we do not know the three-dimensional shape. So then you can integrate the total light. So if I say total equals to you can integrate I as a function of r 2 pi r dr, which is from 0 to, you can say, like infinity, very large distance. Okay. You could also like do that if I as theta is a dependence on it's not symmetric. Like you cannot fit a circle, but you have some kind of objects here, maybe spiral arm, bar, something like that. Then it is possible to like integrate I as a function of r and phi, dr r d phi. Okay, you replace this integral. So basically you get the total light within the image that you see. Once you know the total light, you can calculate the apparent magnitude of the galaxy, which is minus 2.5 times log of 10 I total plus some kind of a 0 point. Okay, 0 point I will write as the C level, some constant. Okay, now this would be also a function of lambda, which is the wavelength, and by the same thing, this would be also a function of lambda, because what you measure are all the wavelength. We do not like in astronomical the measurements. We always measure the light of a galaxy in certain pass bands. Okay, for example, there can be many different kind of pass bands. So you have the telescope, and the photons enter the telescopes and then gets detected in your camera. Or you can have a filter, okay, which will with a certain shape like this, maybe. Okay, so you can say lambda 1, this is like lambda 2, the edge, and this is at lambda naught. So below lambda 1 is 0, and above lambda 2 it's again 0. So so which means the light from this object will pass through only between lambda 1 and lambda 2, this pass band. So these are pass band. So there are various, like, the pass bands and then various filter system possible. So these are in some sense, it's called the filter response curve. Okay. So various filter, for example, if you Google it, SDSS, Sloan Digital Sky Survey, it has like various filters like U, G, R, I, Z. Then there are various filters like B, R, I. Okay, so Johnson and Cousin's filter. There are like any telescope, like you should go and see, check for the filter system is there. You will see a typically response curve like that, which means only photons within this lambda is allowed. So this apparent magnitude from the galaxy is actually depending on the lambda. Okay. Now this is how you calculate the apparent magnitude. Okay. The higher the number, okay, if the fainter it is, higher the number, fainter it is. Okay. For your curiosity, you should check what is this number for the sun. Okay, it will be interesting to look. Now, once you calculate the apparent magnitude, you may want to correct for the dust, because imagine we are sitting at the center of we're sitting on the sun, and then around us, wherever you look, it's like a Milky Way galaxy. So there's a foreground dust, which is around us. So any light from the external galaxies will get attenuated by the dust. So you must correct for the dust attenuation as well. Okay. I'll stop in 5 minutes or so. So imagine now this m lambda, you calculate for lambda, lambda, and then you can calculate another wavelength, which is lambda prime. So two different, there is another filter here. So I'm writing at different. This is like a wavelength here. So two different. One is the lambda, and at the center wavelength is lambda prime. So if you have this lambda and lambda prime, and lambda is less than lambda prime, then you can define color of a galaxy. Color of a galaxy equals to m lambda minus m lambda prime. Alright, so this is how you can define another useful quantity, color of the galaxy. We will come to that, what the meaning of the color of a galaxy. Okay, again, you can see that this is at a shorter wavelength, this is at a higher wavelength. Shorter wavelength, and then this is a higher wavelength. So that's how we define the color of a galaxy. Now, once we do the IR, surface brightness, this plot, of course we can calculate the total light and calculate the magnitude of the galaxy, apparent magnitude of the galaxy. Then of course, if you know the distance, you can actually calculate the absolute magnitude, which is minus m minus 5 log 10 d by 10%. Okay, so absolute magnitude is also possible to calculate, but that's a gross quantity. But we want to know the structure of the light, how the light is distributed in a galaxy. So we already get hold on of this quantity, which is I of R. So you can see the elliptical galaxy here, and on the right side plot, this is plotted as a log of R here, and this is the mu b. Mu b means surface brightness in surface brightness. It's like an apparent magnitude, okay, but at in the B band, B, V, R, I, B band, okay, blue band. And mu b means like this apparent magnitude, so minus 2.5 log of I total. So which means what they do here is like you fit an ellipse here, you calculate the total light. You fit another ellipse here, you can calculate the total light, and then that's how you take. Every time you calculate the total light within a given ellipse, and you can take the logarithm of that with 10 base minus 2.5 times and plus the 0 point, which varies from telescope to telescope, and you can calculate what is the apparent magnitude. And then this apparent magnitude is plotted from the center of the galaxy to outside. You can see 18 means bright, 26 means faint, which means at the center this is like bright and outside it goes faint, so it's like drops. This variation in the light is defined by this function, which is called the Debye-Couleur's profile. Debye-Couleur's profile, or in general, this is called the Sarsik profile, which is if 1 by 4 is replaced by 1 over n. In spiral galaxy, you can do the same thing, and apart from the central part, most of the part are actually following an exponential distribution. Okay, the same thing like this. Once you calculate the IR in this fashion, you can plot, and you will see that the exponential distribution is very easy to see, because imagine ID of R, which I said, and if you take a log 10 of that, it should be basically minus 1 over, what would it be? It's like basically proportional to R, right? So with a constant slope. Okay, so that's why this part is flat, flat. This is like following as a like straight line. So these are fitting down to the data points. But the central part is different. Central part is basically the bulge of the galaxy, and the bulge of the galaxies are, like as I said, 1 over 4 is replaced by 1 over n, and n can be varying from 0 to all the way up to 6 or 7. Okay, so let's keep this part now. Okay, I wanted to get to this plot, and then I stop here. You see the spiral galaxy. This is the kind of a light distribution in the galaxy, and then there is a gas distribution in the galaxy as well. So this is the surface density of the gas, observed surface density of the gas, and as a function of radius. You see, this is where the sun is, and this dashed curve is for the neutral hydrogen gas. And this one for the molecular hydrogen. You can see the molecular hydrogen peak, which means there is a torus of molecular hydrogen at around 5 kiloparsec from the center of the Milky Way Galaxy. And the neutral hydrogen gas stays flat up to around 14 kiloparsec, which was the limit to which we could measure around 78, early 80s. Okay, so that's the limit. And then this is all the plot, and now you can see from 15 kpc we can go up to all the way up to 35 kiloparsec, almost touching the our satellite, which is the Large Magellanic Cloud and the Small Magellanic Cloud. Okay, so neutral hydrogen gas in a galaxy extends very, very far away from the this is the optical light. Means the light from the stars. Okay. And you can see the contours, the density contours of the hydrogen gas extends very, very far away. Okay, almost like a factor of 2 or 3. So neutral hydrogen gas probes very far out the region of the galaxy. And this has been used to infer the existence of the dark matter halo in a galaxy. Okay, this was an observation. For example, in a galaxy in JC 3198, you see the stellar light falls like this at a radius of around 15 kiloparsec. This is the circular velocity. The circular velocity of the hydrogen gas, which is going around the center of this galaxy. Okay, and as you go outer radius, the circular velocity remains constant. This is called the flat rotation curve of the galaxy. And as you can imagine that if we have only sun, and you go around the sun with the mass m, so your bc square equals to gm over r. If this is the distance r, right? So since the mass is constant, solar mass, then as you go further out, the Vc square should fall off. So if you go to the far away from the galaxy, far away from the galaxy, then it velocity, circular velocity should fall like Keplerian pole. So this is a Keplerian pole, but instead it stays flat. So if it stays flat, you need to have some unseen matter. Okay, and one can show that matter will have some density proportional to 1/r². Okay, this can be shown to show the flat rotation curve, and this was been used to infer the dark matter in the galaxy. Okay, so I think I'll stop here, and I see if there is question, then come back. Okay, I see Julie Sengupta. I do not know who asked first because I cannot unmute.
Sir, am I audible?
Yes.
Okay, thank you, sir. So the lecture was really fantastic. So my question was, on the first portion of your presentation, where you were showing the different types of galaxies, there is shown that certain type of galaxies miss the central bulge in them. Is it like they don't even have the central bulge? Is it like that? Like they don't have any high mass object in the center of them? If this is possible, then what is the force, or what is the?
Okay, can we go to the first question?
Like what is holding them?
Oh,
yes. The first question was.
Okay, go ahead, please. Finish your question.
The first question. Yeah, the first question was that is it true that there are certain type of galaxies that miss the central bulge in them? Like absolutely there is
Yes.
no heavy mass core.
Yes, they do. So that's why you see these examples of super thin galaxies. They are observed galaxies, and there are many of them actually. So it's a very and it can be an interesting thing to look at. And now the biggest question is why these galaxies don't form this bulge at the center, right? That's the main question. So it's a very difficult question to answer. The reason is that there are several unknowns that we don't know. Okay, coming to one is that then there will be like a question like, why do some galaxies have bulge? By the way, other question, right? The complementary. So the way the high redshift galaxies go, imagining that these galaxies are coming from the high redshifts and coming now. So in the high redshift galaxy, high redshift in a sense, in this case, around redshift around 1 to 2. That's where we know that most of the galaxies have formed their maximum mass, and this is like a galaxy formation. This is the star formation epoch. So many galaxies are sort of like big clumps and like this. Okay. It's like a lot of the cold gas starting to make stars, the fragments, and then like each of these clumps would go at the center via the frictional force over time. And then they go to the center and maybe form a bigger bulge. Okay, that's the picture we know of for bulge formation in some sense. Of course, there are various other avenues to form bulge as well. For example, I have a very nice galaxy. Apparently, there is nothing like a flat. This galaxy, all of a sudden, merge a satellite, accrete a satellite, and this satellite, because of its angular momentum, go there, spiral into the center, and form a bit of tiny object. It could also for a bulge, right? Our problem to addressing this kind of question is that we don't know what happened. These I can tell you some other avenues to form bulge. Somehow these galaxies, which are very thin, they manage to escape these, and somehow state no, don't want to do interact anywhere, do nothing, just stay constantly mind your own business type. Okay, so we don't know. So that is why it is very difficult to answer even the first question. But I think one should actually. These are also difficult from a cosmological simulation part, because the cosmological simulation do not form such extremely thin galaxies. So they are actually real troublemaker. Even for the, I do not know when these things will be fixed, but this is a normal right now that this could happen, this could happen. There are many other could happen. These galaxies somehow manage to escape. How? We don't know. Does that answer something? Of course, it doesn't answer, but it leads you trouble.
Yeah, it was really helpful. Sir,
okay, but you can read more.
My second part of the.
Yeah, sorry. Okay, just go ahead, please.
My second part of the question was that if the galaxies are missing the central bulge, then what is just holding them together, or what is just providing the power to them?
Okay. So galaxies are bound by themselves. Each of these stars here, sorry, I'm not messing up with this one. These are now stars. There's a phi, which is the potential self. Imagine I have an n point mass, which is like a stars. So it should be like G, Mi, Mj divided with the Green's function. Sorry, the Green's function. A is equal to 1 to n number of stars, I not equals to j. So this is the potential. So if you imagine one star here is like ith star, it will feel force from the rest of the galaxies, rest of the stars in the galaxy. Okay, and this will try to bind themselves. Okay, so this is called the self-gravitational force. Okay, which binds them. There is one more thing. This self-gravitational force plus there is a potential due to the dark matter hit. This entire object would be in terms of the deep potential well of dark matter. Imagine a gas fail and then this galaxy exists at the bottom of the dark matter potential. Okay, so this together sort of holds them together. Okay.
Okay, sir. Okay.
Yeah. Can I go to the next question? Sri Shuman. 1 minute. Can you ask? Shuman?
Yes, sir. Am I audible, sir?
Yes.
Sir, in the 7th or 8th slide, there is a diagram which I couldn't relate the scale. Modern universe to Big Bang, there is Hubble deep field and then radiation era. So could you please explore the diagram?
Okay. Do you want me to go to a slide that I showed to you?
Yes, sir. I think 7th or 8th slide, there is a diagram which shows the scale, time scale from modern universe to Big Bang era.
Okay. I am not able to hear properly, but I would. I'll try to go there so that you can respond. Just a moment. Yeah. I did share. Can you see the screen?
Yes, sir.
Okay, you mean this one?
Yes, sir. Yes, sir.
Okay. Can you now ask what was your question?
Sir, my question is that there is a time scale of the modern universe to Big Bang. So how these things are related? I couldn't relate the above to the time scale.
Time scale. I'm not actually sorry. I'm not able to hear you properly because so in this in this, like universe started with some background, Big Bang, for which like I'm not like an expert. Okay, at some point like it evolved and formed the first stars, like soon after the Dark Age. So there's this the time scale. These are the basically the lifeline of the age of the universe. 13.7 billion years and time 0. Okay, and redshift like the higher redshift to like low redshift. So what time scale you're talking about? Shuman, can you ask once again? Hello? I think I lost. Okay, maybe you can ask me, like, drop me an email with the question. Okay. I go to the next question, Sachin.
Thank you, sir. Sir, can you hear me?
Yes, I can hear you.
Okay. Yes. So my question, when you were discussing about the merging of the galaxies, so my question is, does the merging, if I suppose like two galaxies are merging and both are of spiral, right? Both are of spiral type. So after merging, does it changes shape into new one, like suppose into elliptical one or some irregular one? And what causes it to like earlier one, if the before collision, what causes the galaxy to be in different shapes, like in the irregular form, elliptical form, or spiral one?
This requires to like to go through. The first question is that if the two spiral galaxy merge, okay, then they form elliptical galaxy. Okay, in most cases, when I say that, there are some cases when they would not form spiral galaxy. They may form a lenticular-like galaxy. Okay, now and then there are spiral galaxies in which two spiral galaxies will merge, and sorry. So in most cases, it form an elliptical galaxy, which is like so they lose the spiral structure. That is true, and we know it from the simulation as well. But the next set of questions that you're asking, it is quite difficult to answer just like that, because as if like then we know how the galaxies are shaped by what we see today, right? So because when they form, they are not formed with a spiral structure or elliptical. So
yes.
Okay, so let's keep that in mind, something that we understand, okay? We cannot understand all of your question right now, and it's probably nobody does. So when the galaxies are formed, they are not formed with elliptical or spiral. They evolve to be. Okay, so they evolve to be. Let's like keep that as in the background. Now, as they evolve, okay, there are different processes which will keep them. So one thing that is clear in that, now imagine this picture, suppose I think. Can this picture, which I say at redshift 1 to 2, can this picture lead to an elliptical galaxy or spiral galaxy? That's simple, right? Can this picture lead to? That's the kind of question that would be more focused. Now, I would say that this will depend on how much an angular momentum they be, because the difference between an elliptical galaxy and the spiral galaxy is that it has very little angular momentum. It is basically a lot of angular momentum, in some sense that each of these the spiral galaxy, they are rotationally dominated, means they're supported. So imagine a set of stars, right? Set of stars, they can be going on a circular orbit. This is the picture of a spiral galaxy in general. Okay? So which means that the spiral galaxy are actually rotationally supported. If you don't have rotation, means the centrifugal force, then they would all collapse under gravity. So the equilibrium, in equilibrium, spiral galaxy is supported by rotational force against the gravitational collapse. In the case of an elliptical galaxy, which is like this, then the stars would go like this. This is the kind of orbital structure in the elliptical galaxy. Okay? Many such things. You can draw like many random orbits. The orbits of the star are much more regular, like a circle. Here the orbits are like random orbits. So they are pressure supported. Pressure supported. Now that is the kind of question now. Then why this become a pressure supported? Why they become rotational supported? Which means in the formation somehow it so happened that all the stars came. It probably formed in a very short duration of time, and it's like a really chaos. That's kind of probably happened. Here things are a bit more gradual. Okay, they have time to settle down. Each of them probably going round like that. So I do not know if you get some feeling, but more than this, we need to have some more understanding about these galaxies. Okay, so
Yes.
Okay, so this what shapes the why spiral galaxy is spiral, why elliptical is elliptical. I can give an answer, but if you want to answer from these to these and this to this requires a lots of things. Now, what keeps a galaxy having their own angular momentum? Light, right? So, which means that they are formed in such a way that there's a gradual process must have been happened. So, if you done everything like dump together into in a vessel, so it will form it's like a big mess. So it's an elliptical galaxy in some sense. So there is a formation which is like much more gradual than the elliptical galaxies. Okay, so that's one reason. Then there are several others as it comes all along from your early phase to now. Okay.
Thank you.
You're welcome. I have unmuted.
Am I audible?
Yes.
Yes, sir. My question is regarding the rotational velocity and the distance from the nucleus curve, the dark matter plot.
Okay.
Sir, as it is expected that this flatness should not extend up to infinity, right?
We don't measure. We measure up to a finite radius, so it's not infinite.
So, can this be used to determine the size of the galaxy? Like this is the distance up to which we are observing the flatness, and beyond which we are not observing anything. So, can this be used to determine the size of galaxy?
The answer is no. Answer is no because earlier I would say that one could say that is the end of the galaxy, but that's where we have to measure. Now what happens is that we know that the measurement have its its own limitation, right? So we measure, suppose I want to measure the hydrogen gas cloud. It's going around in circle. Okay. Then I will measure another hydrogen gas cloud. So measure the circular velocity of different radius. Okay. Now, as you go to the farther and farther out, our measurement depends on the sensitivity with which we can measure. Right? Okay. So if it is in a state that our sensitivity and the measurement, with what accuracy you can measure, if we cannot, then it's not possible to measure, but the measurement will stay up to here or maybe here, okay, depending on how good your instrument is, right? So from the measurement of the last point of the flat rotation curve, one cannot say that is the size of the galaxy, because there can be gas which is outside, but we have not measured. Number one, okay, because it's like below the sensitivity limit. There's a one way to think.
Okay.
The other is the growing nowadays, like this, I showed you that image in a coma cluster, the galaxy. So far, they were thinking that the galaxy ends like much before the optical light, the starlight. But I showed you that there is like faint structures like that is coming right outside. Okay, these faint structures, if we can measure the velocity, we may go like also a bit far. Right? So I think how far the galaxy extends depends on what is your sensitivity with which you can measure. Okay. That is from a measurement point of view. Theoretically, you can think about that each of these galaxies, if we know the total mass of the system, then we know what is the virial radius of the galaxy. Okay, so R virial radius of the galaxy. If we know the virial radius of the galaxy, that's when the thing. So actually speaking, the size of a galaxy, which should be such that each of these, whether it's a gas cloud or some star, faint stars, whose energy should be less than or equals to 0. Okay? Moment it is energy greater than 0, which means they are unbound, which means they do not belong to the galaxy. Is it clear?
Yes, sir. And sir, I've also read it somewhere that the distance at which the intensity falls to 0.37 of I naught gives a measure of size of disk. So what is the deal with that?
Intensity falls. Can you just repeat quickly one more time? So to stop.
Sir, the distance at which the intensity falls to 0.37 of I naught, the I naught that we have observed in the intensity plots, gives a measure of the size of disk. So what is the deal with that? Is it identical to virial radius? But I don't think so.
No. Something that I showed here. Just a moment.
Yes, sir. Intensity plot.
This one?
Sarsic profile.
Okay.
This.
Sarsic profile. This one?
Yes, sir. For spiral galaxy, the plot is exponential, right?
This one, yes.
So, sir, I've read it somewhere that the measure of 0.37 of I naught gives a measure of the size of disk.
No, see, there is two size here. This size is a scale length, with which the length scale here is one scale length. The other size that you see here is called the RE. Okay, when R is equal to RE, when R is equal to capital RE, this is 1, 0. So I is IE, surface brightness is equal to effective surface brightness, which means that RE is called the effective radius of the galaxy. Effective radius of the galaxy. Okay, so this is some kind of a length scale in the system. Okay, so that length scale is not exactly, but one can show is very close to like an half-light radius. Okay, it's like a effective radius. You can see if you could just integrate this to R is equal to R, you will get the total light. Okay, and then you will find that integrate up to infinity. Okay, so then this one, when up to integrate from 0 to RE and 0 to infinity, you will see the ratio of these two. Okay, then you will get a sense of RE there. Okay, but RE is called the effective radius in the galaxy. That is a relevant length scale in the problem or in the list. Okay, one last question. I think I should stop because they said that they would I should wind up by 11:50.
Hello, good morning.
Kajal, yes, please.
So my question is like, when we study a galaxy, we study the spectrum of the light which we receive. So how do we distinguish that spectrum which we're studying is coming from which exact galaxy? Like there are billions of out there. So how we
Yes.
distinguish that?
Good. Yes, which I simplify this question. Imagine like now we have a telescope, which is you, and we have an object here. Okay, there can be another object here, just be exactly like we are, right? So how do we know that light is coming from here and not from here? Right?
Yes, sir.
Yes. So this is possible now. So it's not a difficult right now. Which means this galaxy is at a distance something, and this galaxy at a distance is a bit larger distance. Okay. Just by looking at the light, total light, the photons that is coming to your telescope here, and you measure the total light, this thing, you may not see, but you can probably see like lensing structure. There is one way. So you will not see just an image, but there will be lens. The light will bend around here. There's one thing. Other ways, you can take spectra of the galaxy. Suppose this galaxy has some spectral light, because always the stars emit light through the continuum light, lambda, f lambda. Imagine like there is a continuum, and then there is some emission line, and then like this. For example, this is called, suppose this is a like H alpha, which is a hydrogen alpha line. Then this, let's say oxygen 3 triple ionized, like 5,700 angstrom, and then this is at 6563 angstrom. There are many spectral lines that you can observe. So if you have a spectrometer, then you say that you are measuring from this, so you get like this and this, you should mix. But as you know, that the lines that is emitted from this galaxy, lambda E, and what is observed, which is lambda O, the difference between these is 1 plus Z. No? Or in other words, lambda naught, which you observe, is equals to 1 plus Z times the lambda E, which is emitted. Which means if the H alpha line 6563 is emitted at a redshift Z, then observed will be shifted to by 1 plus Z times of that. Okay? This is rest frame, like rest wavelength just. From this galaxy, if we measure the light, they are, because it is a different, this is a redshift Z1 and this is a redshift Z2. So there will be shift. The spectra will identity will be shift there, right? By the shift, we can understand that there are different objects. Okay?
Okay. So there is also a possibility of interference, right? I mean, even interference can...
No. For interference, there is a need for time and then the space together. They are not in the same. They just looks like the photons will come from here at this thing, and then they will be coming like the different. But you're right. I do not know yet. Maybe what if the galaxy is just on top of this? Okay. Maybe.
Yeah.
But in that case, they would be considered. Then you need a very high resolution telescope in which the spectral lines can be separated. Even they are separated by a small amount of delta G. But in principle, this is the philosophy in which you distinguish. Is it clear?
Okay. Yeah. So by studying the redshift factor, we understand which exactly.
Yes, that is the main philosophy. But after that, you say, okay, they are on top of each other. Then we cannot do anything. There can be delta D separation, delta H separation. Then you should have that kind of high resolution telescope which will separate the lines between these two objects. Okay.
Thank you, sir.
Yes. I think there are some questions. I do not know what to do, but I need to go now because then I need to stop. Santosh, are you there? Yeah, who is there? Okay. So how do we get this question? Okay, all these questions that appear in the Zoom. Okay, thank you everyone and see you tomorrow. I log out. I'm sorry. Yeah.